So, saponification is an important organic industrial process. Okay, the first dot point is describe saponification as a conversion in basic solution of fats and oils to glycerol and salsa fatty acids. Okay, the reaction between an ester and a hydroxide ion to form an alcohol and carboxylic anion is called saponification. So it involves a hydroxyl group with an acid with the elimination of water. The natural formation of fats and oils is an esterification reaction, and saponification is the reversal of the process of the formation of fats and oils. And this is a general equation of saponification. You can see how there's a hydroxyl group and the acid. Fat or oil, okay, this is an example of saponification of either a sodium salt or potassium salt or fatty acid salt. The next one is describe the conditions under which saponification can be performed in the school lab and compare these with the industrial preparation of soap. Okay, in the school lab, the soap involves the hydrolysis of a non-poisonous salt like coconut oil or olive oil with the solution of sodium hydroxide before heating and salting out with sodium chloride. The soap produces floats at the top of the solution and is removed and rinsed in water to remove excess sodium hydroxide before being dried. There is no attempt to recover the glycerol, perfume, color, or shape of the soap, and there is possibly a large wastage of reagents. But in industry, however, it's too expensive to use pure oil, and sodium hydroxide is carefully monitored, and it's only slightly in excess because it is expensive. And the saponification occurs in kettles, so large steel containers, in batches under high pressures and temperatures, which can't be done in a school lab. And the aqueous residue left after the soap is salted out and is distilled in order to obtain glycerol, which differs from the school lab, and the remaining salt from the brine is reused. Okay, account for the cleaning action of soap by describing its structure. Water is polar and grease and dirt are non-polar. They do not mix, hence they are immiscible. And this is interfacial tension is a force that separates these two substances that makes them immiscible. Soap is a surfactant, which is a wetting agent that lowers interfacial tension, allowing substance to mix. It is the salt of a fatty acid and has a chain made up of negatively charged polar head, which is this, and an uncharged non-polar tail, which is this. Now the head is hydrophilic, which is water lovely, and the tail is hydrophobic, which is water hating, and it dissolves in grease but not water, whereas the head is the opposite. Now this is the basic action of soap cleaning, and see how the tails attach to the grease or dirt. When that occurs, it forms a micelle, which is basically where the hydrophobic tails attach to the grease, and the negatively charged heads repel each other, which make the grease separate and make it soluble in the water. The next dot point is explain that soap, water, and oil together form an emulsion with the soap acting as an emulsifier. An emulsion is a stable mixture of two immiscible liquids with a dispersion of small droplets of one liquid in another, so for example, water and oil. It is stabilized by the action of an emulsifier, which is the same as surfactant, which lowers the interfacial tension. And soap is an example of an emulsifier. Soap can act as an emulsifier, forming an emulsion when mixed with water and oil by surrounding them with surfactant. The hydrophobic ends are in droplets of oil, which form themselves, and while the hydrophilic ends are attached to water molecules. This causes the oil to disperse throughout the water in small droplets as the hydrophilic ends repel each other because of their negatively charged heads. Now, distinguish between soaps and synthetic detergents in terms of structure of the molecule, chemical composition, and the effect on hard water. Now, soaps are salsa fatty acids, a natural surfactant, which is already been mentioned. And you can see here is the negatively charged hydrophilic group and the non-charged hydrophobic tail. Now the chemical composition, most soaps are sodium stearate. It is a hydrocarbon molecule, so H, hydrogen, carbon, and oxygen. And the head is a carboxylic anion, and the tail is a long uncharged hydrocarbon chain, which has been mentioned. But its effect in hard water, cations in the hard water attach themselves to the soap molecules, tying them up and preventing them from cleaning effectively. So its effect in hard water is minimal, so it's not as efficient. And detergents, there are three types. There's an anion, a cationic, anionic, cationic, and non-ionic. At the structure, it has this benzene an alkyl benzene sulfonate, and the effect in hard water, the surfactant anions form soluble complexes with the magnesium and calcium and reduce the amount available surfactant, but it's not, its efficiency is still greater than soap in hard water. In cationic detergents, the chemical composition, the derivative of the ammonium ion, in which the hydrogen atom is replaced with hydrocarbon alkyl group and 3 short-run methyl groups. Long chain equals oil soluble, and this part is water soluble, and this part is soluble in grease, whereas this part is soluble in water. But its effect in hard water is minimal because basically nothing happens because they are positively charged and repel other cations, so they clean effectively. Now in non-ionic detergents, they have no distinct head or tail because of this, as you can see, and they do not ionize in water. The long hydrocarbon chain connected to one another containing oxygen atoms ending in a hydroxyl group. The chemical composition, the presence of oxygen molecules makes certain sections of the molecule polar, which forms hydrogen bonds with water, while the non-polar tail absorbs the grease fluid, and its effect in hard water is also. Now distinguish between anionic, cationic, and non-ionic synthetic detergents in terms of chemical composition and uses. The chemical composition was mainly mentioned in the previous dot point, but its uses for anionic, it is more effective in soap, and it's used for things like liquid and powder laundry detergents, and soap, shampoo, and toothpaste. Cationic, it cleans plastic effectively, and it's used in fabric softeners as they bond to the negative fabric fibers, leaving a soft smooth feel, and it's also used in hair conditioners, where the positive head attaches to the negative hair scales, and the alkyl tail sticks out, also leaving a soft, smooth feel. And non-ionic, it forms as foam, so it's mainly used for things where foam would be a problem. And it's used in things like dishwashing powder, and it's used a lot in paints, adhesives, pesticides, and cosmetics. The first practical document is perform a first-hand investigation to carry out saponification and test the product. This occurs in a 250 ml beaker, as we have done in the lab. We used coconut oil, and sodium hydroxide and methylated spirits was added and stirred to dissolve. And this was added. And then the sodium hydroxide solution, this was added to the oil, stirring continuously, but it was slowly added to ensure the reaction wasn't exothermic. And the beaker was placed on a hot plate and stirred frequently, wash fast twist over it so it doesn't splatter. And after a thick and creamy look has occurred, 25 milliliters of water is added, and it's poured into a 250 milliliter beaker.
Adam Goss, please come to the office. Adam Goss to the office.
Containing 150 milliliters saturated sodium chloride solution and stirred. And the soap layer. Soap layer is removed and rinsed. Now, the way it's tested, we haven't done this, but from research I've seen that they placed the soap that was collected here in the test tube, while they also placed the same amount of the bar soap, liquid soap, and detergent in other test tubes. And distilled water is added and shaken vigorously in each test tube. And then the pH is determined, and 4 to 5 drops of coconut oil is added to observe how well the oil is emulsified by each. Gather and process and present information from secondary sources to identify a range of fats and oils used for soap making. So common fats and oils used for soap is extracted from coconut, which produces coconut oil, and this is actually a hard soap at lab as well. There's also almond, avocado, cocoa butter, and butter. And perform a first-hand investigation together and describe properties of the named emulsion and these properties to its uses. Mayonnaise is an emulsion of a vegetable oil and egg yolks, with the emulsifier being the lecithin found naturally in the yolk. And it is named by slowly adding oil to an egg yolk while whisking vigorously to disperse oil, and the lecithin stabilize the mixture. It's a very stable emulsion due to the strong emulsifying properties of lecithin. It does not separate into its component liquids, even when stored for long periods of time, which makes it useful as a food product because it needs to stay edible and it needs to be stored for long periods of time. And it has a creamy mouthfeel, which is not oily and adds to its taste. Perform a first-hand investigation to demonstrate the effect of soap as emulsifier vegetable oil, water, and soap is used. 50 milliliters of water, 20 milliliters of oil were placed in the beaker and mixed vigorously. These two liquids rapidly separated because they are immiscible into two distinct layers. And the soap mass was broken into small pieces and added to the mixture. The layers did not separate but formed a cloudy emulsion, and soap acted as an emulsifier and emulsifying two liquids. Solve problems and use available evidence to discuss using examples the environmental effects of soap and detergents use. Soap has minimal environmental impact because it is biodegradable.
Özkan, Obud, Wissam, Adam, Zarif Chowdhury, Ihab Mesa, Muhammad Ahmed, Tariq Girbit, Thomas McNulty, Ibrahim and Osman Hadi, Turain Win, Rami Salah, and Tahsin Zaman. Please go to the hall for ICAS maths exam. Thank you.
Alright guys, soap. It's biodegradable and it's very easily broken down into carbon dioxide and water. And detergents in the early 1950s and 60s were not biodegradable, and they consisted of many branched chains and so caused significant environmental impact. When discharged into the rivers and lakes, they caused excessive foaming, which reduced sunlight entering the water, affecting photosynthesis of plants. But more detergents are biodegradable now because they have a straight, unbranched hydrocarbon chain tail. But phosphate groups are added to soften water to improve efficiency, but act as fertilizers in after bodies, causing excessive growth of algae and other water plants. This causes severe degradation of water quality, the promotion of anaerobic conditions, and the disturbance of the natural ecosystem. Questions. This is a 2015 question. It's a 3-marker, and it says, describe how saponification can be safely carried out as a part of a first-hand investigation. So we talk about many of the safety considerations. So you have to wear goggles because corrosive sodium hydroxide is used in preparation. And 5 milliliters of olive oil or coconut oil is mixed with 5 milliliters of ethanol and 5 milliliters of sodium hydroxide solution in an evaporating basin. Mixture is heated over a hot water bath, or as we did, a hot plate. And after some time, saturated sodium chloride solution added to precipitate the product. And the solid product scooped out with a spatula, washed with water, and then compressed into a small block of soap. For us, it was a different sort of preparation and procedure, but we have to ensure that you talk about safety concerns throughout the whole experiment, not just the preparation, as there are safety concerns throughout the whole thing. The 2009 question, it's only a 2-marker, but it does come up a lot. Explain the cleaning action of soap in terms of its molecular structure. Now, referring to its molecular structure is very common in the industrial part of the HSC exam. So soaps dissolve in water dissociating into an anion derived from a fatty acid or oil, and sodium or potassium cation derived from the alkali used in its manufacture. Sometimes adding a diagram really helps to obtain an extra mark if your sample answer, if your answer was not as detailed. And this is imbecile, as explained before, and how the hydrophobic tail attaches to the grease or the oil. Sometimes adding the structure of the soap itself is also helpful. This is the 5-marker question, and it says, analyze how an understanding of the structure and cleaning action of soap led to the development of synthetic detergents. Again, the structure of soaps comes up again, where the diagram comes in again. And it says soap is a long chain of a fatty acid. The structure has a large hydrocarbon tail, and sometimes adding a diagram helps with the explanation. Dirt is mixed with grease. The non-ionic hydrocarbon end of the molecule dissolves in the grease, and the hydrophilic, water-loving ion again dissolves in the water. This is the basic cleaning action of the soap, which helps to emulsify the grease and wash away. But synthetic detergents were designed to mimic the structure and thus the action of soaps. This is from the last secondary dot point. And the detergent molecule has a long hydrocarbon tail, again talking about the structure of the detergent also helps. And the first detergent had a branched hydrocarbon tail. This was mentioned in the 1950s and 60s, earlier formation of detergents, but they were not biodegradable and thus did not help the environment. And the development of a straight chain tail like the structure of regular soaps led to the second generation of detergents which were biodegradable.